Alrighty, we are going to talk about Michaelis-Menten kinetics real quick. I know when Dr. McKenna explained this in class, it was really confusing because there were a lot of derivations and graphs and just a lot to look at. So we're going to take a step back and start over. Why are we doing this? And what does this even apply to? So Michaelis-Menten deals with enzymes, substrates, the ES complex, which is the enzyme substrate complex when they come together, and the products. All of these factors affect the kinetics of a system. So Michaelis-Menten, I have it abbreviated as MM because I'm lazy and can't spell. It focuses on and only applies to reactions involving enzymes. If there's no enzyme, then this does not apply. So Michaelis-Menten describes the rate reactions with enzymes can occur. So in learning these kinetics, you should understand how changing the substrate concentration or changing the enzyme concentration will affect the reaction at different points in time. So when you get more comfortable with these, try to change the factors and see what happens. Why are we doing this? This is important for biological processes and physiological processes. It helps us define catalytic power of enzymes. It helps pharmaceutical companies in drug development. It, is going to show up on our exam, and it comes back around on the MCAT. I'm not sure about the DAT, but it definitely is on the MCAT. So let's move forward and talk about the equations. We're actually going to start with the assumptions because Michaelis-Menten makes two important assumptions you need to understand. The first one is the equilibrium assumption. This is saying that the formation of enzyme substrate complex reaches equilibrium fairly quickly from the start of the reaction, okay? So it also is allowing us to assume that the formation of products over here happens slower than the dissociation of enzyme substrate back to reactants, right? So it's saying this forward is slower than this backwards, right? So K2 is smaller than K negative 1. Make sure you understand where these rate constants are located on this equation, and by exam time you should be able to write this whole white box out by yourself and understand what it's saying, right? Let's move forward to assumption 2, which is the steady state assumption. I think this one is more common and a little bit easier to understand. So if you're really struggling with the equilibrium assumption, start here and then go back to that one. This one is saying that the formation of enzyme substrate complex roughly equals the loss of that same complex. Okay, so enzyme substrate complex can be lost to dissociation back to substrate, or it can be lost to the formation of enzyme and product. Either way, no matter which direction it's going, this enzyme substrate complex is decreasing. It's either going this way or this way. Either way, there's less of this. Okay. The neat thing about this equation also is that K negative 2 right here is negligible because realistically in our situations we're not going to see much product going back to enzyme substrate complex. It's not really going to go down the K negative 2 route. So a lot of times you'll just see K negative 2 deleted, which is good for us because it's less to look at. But know that it is there, it does exist. So in the early stages of our reaction, we are at a point where we have a lot of substrate and not much product. So we're going to see more of a linear trend with our velocity. And we can define that with this equation down here in red, V naught equals K2 times enzyme substrate complex. So we are going to use this equation for the beginning of the reaction, but not the whole entire thing. We are also assuming the enzyme substrate is going to go this way, down the K2 route and make products, and it's not going to go backwards. And that's what this equation is defining. We're talking about the velocity of this forward right here. This is our initial velocity. This is the simplified version, but since it doesn't apply to all times of the reaction, we have a different equation for whenever our substrate concentration and product concentration starts to increase and decrease throughout the reaction coordinate and the time that our reaction is happening. So like I said, it changes over time. The equations we use in the beginning are not the same ones we use the whole entire time. So the reaction approaches its maximum velocity, known as Vmax, and then we have to use Km and Kcat. I know you guys were confused about the points of these two variables right here, and that's what we're going to talk about mostly for the next few minutes, is the meaning of Kcat and Kn, where they come from, and how they come into play. Like I said, K negative 2 right here is gone because we don't really want to look at it. So I'm going to go ahead and show you this equation right here, the yellow equation. V naught equals k cat times et times s over km plus s, but what does that really mean besides a headache to look at? This is our velocity for our equation. So we are going to look at k cat and km and talk about what et stands for and make this equation a little bit simpler. So the whole entire point of this equation is that we're going to be able to graph this once we take the double reciprocal later on. All right, here's the equation we just looked at. We're going to make it a little bit easier and bring it down here. We're going to look at k cat and at. K cat is the power of our enzyme, and we're going to talk about it later. And et is the total amount of enzyme. So if you have, k cat times et, this is really going to define our maximum velocity, right? So our maximum velocity is going to, take the place of k cat and at. We can make this substitution because max velocity is dependent on the enzyme's catalytic power, right? So it's power over here times the amount of power of our enzyme is going to define our Vmax. So we're just going to make it simpler to look at right here. Like I said, ET is the total amount of enzyme, and that equals the free enzyme plus the enzyme substrate complex concentration. All right, now we're going to look at Km real quick, and this is our Michaelis constant. So where does Km come from, and what is it? It comes from all of our reaction rates up there at the top. So we're saying that Km equals the backwards reaction to substrate plus the forward reaction to product divided by the creation of enzyme substrate complex. So it's the, the rate constant that we are losing enzyme substrate complex divided by the formation of enzyme substrate complex, all of these rate constants. But Km is a substrate concentration and not a rate constant. All right, so keep that in mind that capital K is not the same as this lowercase k. We're going to go ahead and further define Km as the point in which we reach half of Vmax. We're going to look at that on the graph right here. So Km is right here, and we're going to find it on the graph by doing this. We're going to go up to Vmax. We're going to say, okay, if Km equals half of Vmax, let's find half of Vmax. Okay, Vmax, we're going to go to half. Vmax over 2, same thing as half of Vmax, right? We're going to follow our dotted line and drop it down, and suddenly we are at Km, okay? So we don't follow the x-axis first, we follow the y-axis, okay? Find Vmax, find half of it, and this is how we're going to define Km, okay? Be comfortable looking at this graph right here and understand that Km is a substrate concentration. It is not a rate, it is a concentration down here on the x-axis, okay? Now, with all of these variables, we want to know, is it better for them to be higher or lower, and why are we using them? So Km is one of the ones that we want to actually be lower. And why do we want it to be lower? That's because down here where Km is, we can say that if Km is lower, then we need less substrate to reach half of Vmax, right? So if our Km right here was way over here, it takes a ton of substrate to reach half of Vmax, right? But if our Km is way over here close to 0, then we're only using a little substrate to reach half of our maximum velocity, right? That's saying our enzyme is doing pretty good. It reaches that half Vmax pretty quickly without adding a ton of substrate. But we can contrast this over here with kcat. So kcat is the turnover number. It's commonly talked about in terms of catalytic efficiency, but you want to be careful describing it that way. It's most accurately defined as turnover number. So it does help describe efficiency, but it is turnover number. Higher values for this are better and, different from Km. You want the kcat to be higher because it talks about a more efficient enzyme that can react with more substrate in a given time period. So since kcat is our maximum turnover number, it actually is defined for an enzyme, so it's not really going to change, but it's also the limiting rate constant of our reaction. So this is straight off your slides, and make sure you remember the relationship between kcat and turnover number and the fact that it does, it is a limiting piece of our reaction. So like I said, kcat is not necessarily catalytic efficiency, but it's very closely related. It does help describe it. So catalytic efficiency is better described as kcat over km. This expression defines the specificity constant, and this is important because it allows us to compare enzymes across the board, right? So we can compare different enzymes and concentrations across the board, not just one reaction, but it gives it a point to say, is this enzyme more efficient than this other enzyme in this situation? But just remember Kcat over Km, not the other way around. Remember, Km is not a rate, but Kcat is a rate constant, okay? So we're going to move away from specificity constant and look back at this V naught equation right here. Okay, so this is kind of hard to graph. So we're going to bring it down to y equals mx plus b form before we graph it. So let's go ahead and start. We're going to take the double reciprocal. So that means we're going to take this one, and this is v over 1. We're going to flip it upside down. And we're going to flip this one upside down, which we did right here. Okay? So we now have the double reciprocal. This is fine, but again, this one's not necessarily easy to graph yet, so we're going to bring it a little bit further and simplify it more for you. Okay, so we're going to come over here. We're going to split this fraction in half. Both pieces of the fraction are going to have v max times s as our denominator. So right here, or on the left side of our equation right here, we're going to have, or the left side of the plus sign, I mean, we're going to have Km as the numerator, and then on the right side, we're going to have the substrate as the numerator, and both sides are going to have v max times s as the denominator. When you come over here and simplify it, you get this right here. It's kind of confusing to look at first, but I promise it does simplify this way. This, again, lots of fractions going on, but the cool thing is that now it's in y equals mx plus b format, right? Here's y, here's x. This is m, our slope, and this is our y-intercept over here, 1 over v max. So even though this is, not that fun to look at, it does make it easier for us to graph. If we come over here, we have our graph right here, and this is now linear, right? This is better than some crazy looking graph from our original V naught equation, but we've manipulated it so that we can look at it easier. We're going to have our x-intercept as 1 over km. Our y-intercept is going to be 1 over v max. The slope is km over v max. So if you know this equation up here at the top, this double reciprocal equation in y equals mx plus b format, then we are graphing this right here. So if you can look at this graph, you can pick out the individual pieces, the x-intercept, the y-intercept, you can calculate the slope. Yeah, so this is really good because, Dr. McKenna could show you this kind of graph and ask you to find one of these different variables or, do some kind of manipulation of the equations. But if you have this graph and you know how to read it, then you're good to go because you know that even though this is really scary and there's lots of fractions, all it is the double reciprocal version of the equation, right? We just manipulated it so we can use it better and graph it better. And that's what you want to get comfortable with whenever you're studying, is you want to get comfortable looking at these kinds of graphs without saying, oh my god, I have no idea what this is, right? So now that you've had, a basic breakdown of the equations and the different variables, go back to McKenna's slides and start studying those a little bit more in depth. As always, let me know if you have any questions. I am happy to help, and happy studying.